Okay, hopefully this will wrap up chapter 17. We are in section 17.4, solubility equilibria. You'll recall from Chem 1 in chapter 4, you had a solubility table that listed whether compounds were aqueous or did not dissolve in water. They would have been classified as solids. They were insoluble. And so this concept applies to insoluble compounds. For example, silver chloride. Silver chloride is AgCl. Now, even though silver chloride is insoluble in water, there's a very small amount of it that will dissolve. And so if you were going to write a solubility equation for silver chloride, these are still equilibrium equations. And it would look like this. Okay, another example, barium carbonate. I'm going to leave some space under that one because I'm going to come back and do more to it in a minute. Barium carbonate. Could you pause the video and write its solubility equation? And that's what you should have for barium carbonate. I'm going to change slides and do one more, calcium sulfate. Why don't you pause the video and just write the solubility equation for calcium sulfate and then start it back up and see. Okay, and there's the solubility equation for calcium sulfate. Now, because each of these, they're always written as equilibrium equations, then you can write an equilibrium constant expression for these, which is, you know it, we've been doing it for several chapters now, products over reactants raised to the power of the coefficient. So the equilibrium constant for this looks like, well, the product of the silver ions times the product of the chloride ions. And those are the products over, and you don't include the reactants because there's a solid. Because these are solubility equilibrium, they are labeled as a KSP. A KSP stands for solubility product constant. Okay, so the KSP for barium carbonate, the expression would look like this. The barium ions times the carbonate ions. And then as we do that third one, the KSP for calcium sulfate is the calcium ions times the concentration of the sulfate ions. Now, when we do calculations involving KSPs, there's a table in your book. Table 17.4 in your book is the solubility product constant table. So it gives the KSPs for these compounds. For example, the KSP for silver chloride, this is what the expression looks like. If you look up the KSP for silver chloride, you will find that it is 1.6 times 10 to the minus 10. And again, that's unitless because equilibrium constants do not have units. The KSP for barium carbonate is 8.1 times 10 to the minus 9. And you need to be familiar with looking these up yourself because when it comes time for the test, and possibly on Connect, you're going to have to look them up. I know you will on the test. And then calcium sulfate, its KSP is 2.4 times 10 to the minus 5. And so that's the KSP just from the table. Now we are going to, for silver chloride, the problem might say calculate the molar solubility of silver chloride. calculate the molar solubility of silver chloride. And so that's all the problem's going to say. You should know what the formula for silver chloride is, and you should know how to write this equation and this KSP expression just using these words, calculate the molar solubility of silver chloride. You would need to look up on the table the KSP. And if you look that up on the table, you'll find that table gives you a lot more information. So here's how you would work a molar solubility equation. I'm going to show you with an ice table, and then I'm going to do the barium carbonate with an ice table, and then I hope you guys can see the pattern. And maybe you won't have to set up the ice table every time. Okay? So the idea is you start with some solid silver chloride. Okay, so we just have some of this. It doesn't matter how much. The reason it doesn't matter how much is because this is a solid and it's not going to show up in this expression. But we need this to get started. Now, we don't start out initially with any silver or any chloride. Some of this silver chloride ionizes. X amount of it ionizes. And so you know that once we know on that change line one number, and we do, it's just X, then we know that we'll make X amount of silver and X amount of chloride, because I'm following along with the stoichiometry. Remember, 1 and 1. If one of these had a 2 in front of them, we would have to say 2X. Okay, so at equilibrium we have something here, but it doesn't matter because it's a solid. At equilibrium we have X amount of silver and X amount of chloride. So if we plug in to the KSP expression X for silver and X for chloride, do you guys see that the KSP is equal to X squared? That means 1.6 times 10 to the minus 10 is equal to X squared. When you solve for X, you have the molar solubility. So to solve for X, you simply take the square root of the KSP. And so for X, I get 1.26 times 10 to the minus 5 molarity. X is 1.26 times 10 to the minus 5 moles per liter. And you could write that as molarity, or you could write that as moles per liter. Okay, so let's do the same thing for barium carbonate. The problem would say calculate the molar solubility of barium carbonate. Do you see that the ice table is going to be set up the same, where we have some barium carbonate, X amount of it ionizes. So at equilibrium, we have X amount of barium and X amount of carbonate. So again, we end up with the KSP, 8.1 times 10 to the minus 9, is equal to X squared. And X is the value of the molar solubility. So we just have to take the square root of 8.1 times 10 to the minus 9. And so the molar solubility for barium carbonate is 9 times 10 to the minus 5 moles per liter. It's important that you include your units on that. Okay, you don't have, the KSPs do not have units, but molar solubilities do. So the last one, calculate the molar solubility of calcium sulfate. And so I get, I've realized without doing the ice table that all I need to do is take the square root of 2.4 times 10 to the minus 5. And then I get that the molar solubility is 4.9 times 10 to the minus 3 moles per liter. And that's the molar solubility. Okay, molar solubility is in units of moles per liter or molarity. Now, some problems might say calculate the solubility. That is different than the molar solubility, simply leaving out that word. So calculate the solubility of calcium sulfate. It's the same thing we've done, except solubility means that we need it in grams per liter, not moles per liter. So typically, if you needed to calculate the solubility of anything, you are going to first calculate the molar solubility, which we did here. And then to go on and calculate the solubility, you're going to take that number, 4.9 times 10 to the minus 3 moles per liter. And do you see that to calculate the solubility, it's simply a moles to grams conversion. So it is simply a molar mass. A mole of calcium sulfate is equal to, calculate the molar mass of calcium sulfate. Okay, so calculating the molar mass of calcium sulfate, I got 136.15. So to get the molar solubility, I simply solve that. And the molar solubility is 0.67 grams per liter. That's the solubility of calcium sulfate. Okay, now I'm going to take a small picture of the KSP table so that we can all be looking at it together and I can underline things on it. Okay, I say small picture because I can't get everything in it, but look. Can you guys look at that and tell me, let's see, we just did calcium sulfate. See, that's an X squared. You can look at it and tell. So go down the line. What else is X squared? Pause the video, go down the line, and then start it up and see if you're, because I might be moving faster than y'all are moving. I can't tell because I can't hear you answering. Find the other X squared ones. Okay. Barium carbonate's an X squared one. Barium sulfate's an X squared one. Cadmium sulfide. Calcium carbonate. Cobalt 2 sulfide. Copper 1 bromide. Copper 1 iodide. Copper 2 sulfide. Iron 3 phosphate. Iron 2 sulfide. Okay, y'all, all of these are X squared ones. Do you see that they're X squared? Because every one of them's underneath their ice table, it's all going to look the same. So for every one of those I've underlined in green, to calculate the molar solubility, you just take the square root of the KSP. And then you multiply it by its molar mass to get to solubility. It's boom, 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 over and over and over. Okay, now let's go one step up from that. I consider it one step up. Let's look at this one. Barium fluoride. Okay, and I'm going to go to the next slide. The table has it, but if you don't have the table, guys, you should still be able to write the equilibrium, dissolution for barium fluoride. Okay, you should know that it's barium and 2 fluorides. And of course, that's going back to like doing net ionic equations in Chem 1. So if we set up an ice table, pause the video and set up the ice table. Then check here with what I write. Make corrections as needed. See if you can understand what you missed. And then we'll go the next step. Okay, now you've started the video back. So we've got some barium fluoride. X amount of it ionizes. We don't start with any barium. We don't start with any fluoride. I know that if I have X amount of barium fluoride ionizing, then I'll make X amount of barium and 2X amount of fluoride. Okay, now walk through the KSP expression. The KSP expression looks like this. It's the barium concentration times the fluoride ion concentration squared. Remember, because you have to raise those to the power of their coefficient. Now, I want you to plug in your X's for that. Pause the video and plug in X. And then when you start the video, you should have plugged in this. X and 2X squared. Then when we condense that, we'll see that the KSP is equal to 4X cubed. So on this one, in order to solve for the molar solubility, we're going to have the KSP, barium fluoride, is 1.7 times 10 to the minus 6 is equal to 4X cubed. So first we have to divide by 4 Then we have to take the cubed root of our number to figure out x. So I'm going to take 1.7 times 10 to the minus 6 and divide it by 4. And I get 4.25 times 10 to the minus 7. And then I'm going to take the cubed root of that. And for x, I got 7.52 times 10 to the minus 3 moles per liter. That is the molar solubility of barium fluoride. To calculate the solubility, you guys set that up, pause the video, and do that. And then when you start the video back, you should have written 7.52 times 10 to the minus 3 moles per liter times, for the molar mass of barium fluoride, I got 175.3. And I'll multiply that out. And I got 1.32 grams per liter. So, here's my molar solubility. And then here's the solubility. Okay, so that one wasn't an x squared. Do you see why it was 4x cubed? Look at the table and let's go through. Pause the video, go through, and identify all of them that are 4x cubed. And then when you start it back, now you're starting it back, so you should see calcium fluoride's 4x cubed, calcium hydroxide, copper 2 hydroxide. That's all the ones right there that are 4x cubed. Okay, next, can you guys figure out what this one is on your own? See, it's a 1 and a 3. Do an ice table, and what I'm wanting you to figure out is what this one's going to be. Like when it's 1 and 1, see, it's x squared. When it's 1 and 2, it's 4x cubed. I want you to figure out what it is on this one when it's 1 and 3. So pause the video and figure that out. Then when you start the video back up, here's what you should have. And that part you could have gotten from the KSP table. See, it's got that on there, but we don't need that from the table. We can do that. Okay, and so we knew that the KSP is equal to the concentration of the aluminum ion times the concentration of the hydroxide ion cubed. And so, see, the aluminum concentration at equilibrium is X. The hydroxide ion concentration is 3 times that, but I still have to cube it. And don't make the mistake of cubing 3 and getting 9. But the KSP is 27x to the 4th. Because 3 cubed is 27, and x times x cubed is x to the 4th. So, going back to the KSP table, anytime you see a 1 and 3, you're going to have 27x to the 4th. Oh, I see that I missed one earlier, didn't I? Or did I erase it? I missed this one as an x squared earlier. But all the purples are x to the 4th. So, if we calculated the molar solubility, we would say that 1.8 times 10 to the minus 33. That's a really small number, guys. Do you see? Times 10 to the minus 33. That means aluminum hydroxide. It doesn't dissolve in water, but even if you had it in water, very little of it is going to dissolve. Okay, the larger the KSP, the more that dissolves. The smaller the KSP, like this one, you're talking a very small amount of solubility. So to solve for the molar solubility, the first thing I do is I take that number and I divide it by 27. And then I take the fourth root of that. When I divide it by 27, I got 6.67 times 10 to the minus 35. And then I take the fourth root of that to get the molar solubility as 2.86 times 10 to the minus 9 moles per liter. Okay, and so that's a really good foundation on the KSP and the molar solubility and solubility. There's a couple practice problems in your book, sample problem 17.7. But continuing on with this idea, we're still in section 17.4. Let's look at predicting precipitation reactions. Okay, and you wrote precipitation reactions in Chem 1. You know, the double exchange reactions, like you would take like an AX plus a BY. Remember doing this? AX plus BY yields AY plus BX. And you looked at the solubility table and you decided what was soluble and what was insoluble. Okay? And this is similar to that, except, guys, in order to make a solid form, you have to have a saturated solution. You've got to have enough of your two reactants to make a solid form. If they're diluted, you can actually mix things and a solid will not form. So that's what we're doing here, is actually calculating, will there be a precipitate? And so here's, I'm just going to work a problem with you, and that's how we're going to practice this. Okay, I'm going to do this. Let's predict if a precipitate will form if 650 milliliters of 0.0080 molar potassium sulfate is added to 125 milliliters of 0.0058 molar barium chloride. The first thing we need to do is figure out what the precipitate is. So to do that, we've got to write an equation for potassium sulfate and barium chloride. So potassium sulfate and barium chloride are both aqueous. And I know that really from my solubility rules, because we have those. Also, in a problem like this, the things you're mixing are the aqueous things, okay? That's how you know as well. The products of this are barium sulfate and potassium chloride, and there it is balanced. And which one of these is going to be the precipitate? Well, in Chem 1, we use the solubility table, which you can still use here. But also you have that KSP table. Only one of these is on the KSP table, and that's the barium sulfate. So that's the precipitate, okay? This is aqueous. If you will remember also that anytime there's a group 1, anything from group 1, that's always aqueous. So that was our first job, is to figure out the precipitate. The precipitate, when we say predict if a precipitate will be formed, we're asking, will barium sulfate, will it precipitate? Then we're also going to need the KSP for that. The KSP for barium sulfate is 1.1 times 10 to the minus 10. And we know from looking at the KSP table, we know that barium sulfate's solubility equation would look like this. barium ions and sulfate ions. We know that its KSP expression would look like this: barium ions and sulfate ions. And we know it's an x squared, okay? We're not actually going to need the x squared for this one. So, will a precipitate form? What we're going to have to do is calculate Q. In a minute, I'm going to have to switch slides, guys, because I'm not going to be able to fit everything here. Do you remember we've done Q before? Q is a reaction quotient. We used it in equilibrium to tell which direction the reaction was proceeding to achieve equilibrium, okay? Q is calculated exactly like the equilibrium constant. It's the concentration of the barium times the concentration of the sulfate in this example. What we have to do is we have to calculate the Q. We're going to calculate it on the next slide, and we've got to compare it to the KSP to see which number's bigger, to see if a precipitate will form. So how do we calculate the Q? Where do we get the concentration of the barium from? Do you see that in this problem, the barium is coming from the barium chloride? To calculate Q, I'm going to try to copy this and paste it on the next slide so I can use it. Okay, to calculate Q, we need to know what is the concentration of barium in this solution and what is the concentration of sulfate in this solution. So I'm still calculating Q, but the concentration of the barium comes from the barium chloride. We're going to do an M1V1 equals M2V2, where the barium chloride concentration is M1. It's 0.0058 molar. The volume of that I'm using is V1. M2 is the concentration of the barium. That's what I don't know. V2 is the total volume. The total volume is the 650 plus the 125. So the total volume is 775 milliliters. Because I want to know when these are mixed, what's the concentration of barium. And so I get, for concentration of barium, I get 9.35 times 10 to the minus 4 molar for the concentration of barium. Now, what I'm doing, I've got the barium. It's 9.35 times 10 to the minus 4. Now I need to calculate the concentration of the sulfate. So you guys see if you can use the barium one as an example and set up the sulfate one and solve for it. Pause the video and do the sulfate. And when you start the video back up, we will work through sulfate together. So M1 is 0.0080 molar because it's the potassium sulfate. V1 is 650 milliliters. M2 is going to be my sulfate, and V2 is still 775 milliliters. So for the concentration of sulfate, I get 6.71 times 10 to the minus 3 molar. So when these are mixed, that's the concentration of the sulfate. It's always going to go down from what you started with because you're combining it with something else. You're diluting it, but you're not diluting it with pure water. You're diluting it with a solution of something. So 6.71 times 10 to the minus 3 is this number, the sulfate. And now I'm ready to calculate Q by multiplying the 9.35 times 10 to the minus 4 times the 6.71 times 10 to the minus 3. And for Q, I get 6.27 times 10 to the minus 6. Now I'm going to compare these two numbers, the KSP and the Q. Which one is bigger? Q is bigger than the KSP. If Q is bigger than the KSP, then yes, a precipitate will form. If Q is smaller than the KSP, then no, a precipitate will not form. Okay, and that's how you predict a precipitate. There's more problems like that. Sample problem 17.9. And I actually used the compound from part of that. Sample problem 17.9 uses potassium sulfate and barium chloride in A. I did change the numbers for the barium chloride, but there's more practices with those, so you guys can see and practice more of those. Okay. Next section, chapter 17, is section 17.5, factors affecting solubility. Okay, the first thing we're going to look at in that section is the common ion effect. If you'll remember, we did this when we were introducing buffers at the beginning of this chapter. Okay, and we introduced that Henderson-Hasselbalch, that buffer equation. For example, earlier we were calculating a solubility. So let me pull a different one from what we've done. This is a redo before we do common ion. Can you guys calculate I want molar solubility. Of lead 2 carbonate. Look it up on the table, decide if it's an x squared or 4x cubed or 27x to the 4th, and calculate the molar solubility. Pause the video and do that. And when you start the video up, you should have looked up that the KSP is 3.3 times 10 to the minus 14. You should have recognized that that is an x squared one. So simply the square root of that gives me the molar solubility, which is 1.82 times 10 to the minus 7 molar. Okay? And when we're calculating it like that, calculate the molar solubility, we are calculating the molar solubility in pure water. Now, what if we change that equation, or that question, to say, calculate the molar solubility of lead 2 carbonate in 0.10 molar sodium carbonate. Oh, yeah, I wrote that right. Calculate the molar solubility of lead 2 carbonate in 0.10 molar sodium carbonate. So the first one that we have written in black, that was in pure water. But now we're in a solution that has a common ion. You can clearly see that the common ion is the carbonate. So how has this worked? Well, I'm going to move back up under this other one. Y'all know that this KSP was arrived at by taking the concentration of the lead times the concentration of the carbonate. Okay, and we plugged in x and x and got x squared, and then we took the square root of the KSP. But if we have 0.10 molar sodium carbonate, That means if that ionizes completely, and it does, if all of this ionizes, and you don't have to write this, I'm doing this so you can understand where I'm getting the numbers from. You see my ice table? When all is said and done, if I start with 0.10 molar sodium carbonate, then I've already got 0.10 molar carbonate in the solution. See, the sodium's not going to matter. Not because it's a solid, but because in this example, it's a spectator ion. Sodium is not the common ion with the lead 2 carbonate. What we have to do is figure out in 0.10 molar sodium carbonate, how much carbonate's there. Well, it's 0.10 molar. So that means when we have our KSP for lead carbonate, and I'm going to go to the next slide to finish this because I need more room. Here's what changes. And again, I'll do an ice table to show you where it's coming from, and then when I plug it into the KSP, hopefully you'll see it's very simple. Well, still, if we're doing an ice table, none of this matters. But how this one's different is even though we're not starting with any lead, in this one, see, we're starting with carbonate. So it's not 0. So it was an x squared one. We're still going to have x amount and x amount here. And at equilibrium, we'll have x amount of lead and 0.10 plus x amount of the carbonate. So the KSP, which is 3.3 times 10 to the minus 14, it's equal to the concentration of the lead times the concentration of the carbonate. And in this example, the lead is x and the carbonate is 0.10 plus x. And we make the same assumption that we've already made with weak acids and weak bases, that x is going to be really small. And so adding it to 0.1 is going to be irrelevant for the calculation of this equation. So we solve for x. To solve for x, you simply take 3.3 times 10 to the minus 14 and divide it by 0.1. And for x, we get 3.3 times 10 to the minus 13 molar. And you can see that if we had that number to begin with and plugged it in for x, it would not have mattered to that equation. And so that's the molar solubility of lead 2 carbonate in a solution with a common ion. So look, when there was carbonate there, the molar solubility is this number. If we look back at our previous problem, when it's in pure water, the molar solubility is this number. This 1.82 times 10 to the minus 7 is a bigger number. In other words, more dissolved in pure water than will dissolve with a common ion, which is usually the case. Okay, and so there was a lot of explanation on that one, but we're going to do another similar one with the common ion. And hopefully now we won't need all that explanation. So first, let's calculate the molar solubility. We'll do silver chloride in water. If I just said silver chloride, it's understood to be in water. And then let's calculate the molar solubility of silver chloride in 0.05 molar sodium chloride. Okay? So pause the video and just do this one, the first one first. And you should have gotten for the molar solubility 1.26 times 10 to the minus 10 when it's in pure water. Now let's look at it in sodium chloride. The KSP is equal to the concentration of the silver times the concentration of the chloride. The KSP is 1.6 times 10 to the minus 10. The silver is X. The chloride is the common ion, and this one's going to be 0.05 in chloride. The sodium's a spectator ion. So the solubility in sodium chloride, it should be smaller, and indeed it is. It's 3.2 times 10 to the minus 9 molar. Not as much dissolves when there's a common ion there. We decrease the solubility. Okay, the next part of section 17.5, factors affecting solubility. Let's look at pH effect on solubility. pH affects the solubility. And how pH affects the solubility, it depends on the solubility, on the pH of what you're dissolving. And so I'm not going to work on calculations with these. We're going to work at conceptual. For example, on your solubility table, magnesium hydroxide is listed. Okay? Y'all, magnesium hydroxide, dissolving that in solution, is it going to be an acidic solution or a basic solution? It is easily identified as a basic solution. It's hydroxide, okay? So it has a basic pH. So to get more MgOH2 to dissolve, we should increase the pH of the solution. So if the solution is basic, you want to increase the pH to get more to dissolve. If we decrease the pH of the solution, I just said it wrong. I just said it wrong, guys. About 43. Okay. So to get more magnesium hydroxide to dissolve, if it's basic, that means a high pH. We need to decrease the pH of the solution. So to get more soluble, basically you identify the pH of your salt. You go the opposite way to get more to dissolve, okay? If the pH, this is where I caught my mistake. If the pH is increased, okay, increased means more basic, then less salt dissolves. And the salt here is the MgOH2. Okay, so how pH affects the solubility is you identify the pH of the salt, and if the pH goes more towards what the salt already is, then it's going to be less soluble. If the pH moves away from what the salt is, then it's going to be more soluble. So this goes back to chapter 16, when we looked at salts and we decided first whether the salt is acidic, basic, or neutral. For example, like potassium chloride salt. Well, if you'll remember, you have to decide what was the strength of the acid and what was the strength of the base that made potassium chloride. Potassium chloride can be formed from potassium hydroxide and hydrochloric acid. Both of those are strong. That means this is a neutral salt. That means changing pH will not change the solubility. For any neutral salt, changing the pH will not change the solubility. Okay? Let's take ammonium bromide, for example. Well, you should recognize that bromide comes from a strong acid, hydrobromic acid. So that's not going to do anything to pH. But then you say, well, ammonium comes from ammonia, which is a weak base. Ammonia is a weak base. Ammonium is its conjugate acid. So this is going to be an acidic salt. So increasing pH makes it more soluble. Decreasing pH makes it less soluble. And it is the salt. It each time is the whatever I'm talking about. Makes ammonium bromide less soluble. Okay. Then if we look at the salt lithium fluoride, is lithium fluoride an acidic, a basic, or a neutral salt? Well, lithium comes from lithium hydroxide, which is a strong base. So that has no effect on pH. Fluoride comes from hydrofluoric acid, which is a weak acid. So fluoride is the conjugate base of a weak acid. So this is going to be a basic salt. It's basic because of the fluoride. So a basic salt increasing the pH makes the salt less soluble, and decreasing the pH makes the salt more soluble. Okay, the next part in your book talks about complex ion formation. And guys, I'm not even going to cover that here. You practiced that concept in lab when I gave y'all, it was one of the last labs we got to do, the silver, mercury, lead, and you got to see the positive test for silver and mercury and lead. It was a complex ion test. If you were in front of me, we would talk more about that. But I think having done that lab is sufficient for that. So that is going to conclude chapter 17. Okay, and I selected a few end of chapter 17 for you to practice. As we've lectured, I've mentioned problems in the chapter, so you can always work those. 5, 9, 15, 35, 51, 53, 57, 63, and 65. And that will conclude the material for the test. Be sure you watch my video about what the test is going to be like, and be sure you take that practice test before you do the test. I want you to know it's just 3 questions to work, and you have to upload your work as part of the test in order to receive credit for your answers. And that's all for now.